Hello everyone and welcome to the second lecture in the series on diffusion model. So this is the second video in this series. In the first video we looked at variational autoencoders and evidence lower bound. In this video we will be starting with diffusion models. So we'll try to see how the evidence lower bound works out for these models, and we'll see a problem with the first approach, and then we'll also look at another approach. In the third and the final video, we'll conclude with the algorithm for the same. So let's get started. So last time we saw that for a latent variable model, wherein we defined the distribution of x as integral over z pz px given z dz, right? So we saw that log of px could have been expressed as maximum over all distributions q, the evidence lower bound expectation over q log pxz by qz, right? And now we'll see that, okay, what happens, if we try to extend such a latent variable model. So the first thing which we look at is the hierarchical variational autoencoder, which we'll abbreviate it as HVAE. Okay. So here essentially what we have is that instead of a single latent variable which defines the distribution, we have a sequence of latent variables. Right? So we have a sequence of latent variables forming a Markov chain which captures the full distribution. So here first we have a latent variable zt, which is normally distributed with mean 0 and covariance identity. Right? Conditioned on zt, we have zt minus 1, and then all the way up to x, which is our data. Right? So essentially we have t latent variables z1 up to zt, and overall the joint distribution is defined via this Markov chain. And so it looks like as follows, that we have p of zt, right? And then we have product of t from 1 to capital T, p theta of zt minus 1 given zt. Right? So here essentially we are defining z0 as x. The data itself we are calling as z0, although it's not a latent variable, but just for ease of notation and ease of writing this product, I just called it z0. Now in this case, right, so here essentially hierarchical VAE is a sort of a is a model wherein we have a Markov chain of our latent variables, right? So corresponding to this, we can define a posterior distribution which is given by q phi of z1 up to zt given x, right? Now since z1 up to z capital T and x, they form a Markov chain, right? So do x. Okay, so here essentially I had zt, zt minus 1, z1 and then x, right? So the chain, the ordering was that you start from zt minus 1 and then you start from zt and then go all the way down to x. So we have zt minus 1 dot 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 z1 and then x. Now the thing is that if I take the reverse order, they will also continue to form a Markov chain. So in reverse order, the latent variables are x, z1, z2 and then finally z capital T. Now since even in the reverse direction they are forming a Markov chain, so if I have to write down the posterior distribution q phi, which is z1 up to z capital T given x, that can be expressed as product of t from 1 to capital T q phi zt given zt minus 1, Right. So here essentially I'll actually all these zt given zt minus 1, for every t I have a different distribution, so I'll superscript it with t. Right. So here again I'm calling z naught as x. Right. So I'm calling x as z naught. Right. Because essentially firstly what I'll need is that z1 given x. So here that I'm writing is z1 given z naught. Now as before, what I have is that the log px, so this is greater than equal to ELBO, which I write as expectation over q phi z1 up to z capital T given x log probability of x and z1 to t over q phi z1 to t given x. Right. So this is my ELBO or evidence lower bound. Right. So this is essentially how the hierarchical variational autoencoder is defined. Now when we move on to diffusion models, the variational diffusion models, so essentially a variational diffusion model or VDM is a hierarchical variational autoencoder, right, with following constraints. So what are these constraints? Let's have a look at these. Firstly, what we have is that the top latent variable z capital T is normally distributed with mean 0 and covariance identity. Well, this looks natural, but then we also have that q of the posterior distribution q of zt given zt minus 1, right. So this is essentially normally distributed with mean root alpha t zt minus 1 and covariance 1 minus alpha t identity, right. So here alpha t is my hyperparameter, right. Now what we have additionally over here is that since basically zt I define the mean as root alpha t zt minus 1, this essentially implies that dimension of zt is same for all t, right, which is also same as dimension of x, right? Because x is essentially z naught, what we have been calling it by z naught. Now the typical convention in variational diffusion models is that we stop using the variable z, but we start using the variable x. So here we have a chain of variables xt, xt minus 1 up to x naught, and x naught is my data. Okay, so these are all the latent variables. So the question is that how to compute this evidence lower bound. Well, let's start with the definition. So we had already derived the latent evidence lower bound when we looked at the hierarchical variational autoencoder, and we saw that this is defined as greater than equal to expectation of q phi x1 to t given x naught log probability of x0 to t over q phi x1 to t given x naught. Okay, so now let's expand. How does this look like? So this is nothing but expectation for q phi x1 to t given x naught. Okay, now I have log of probability of xt times t from 1 to capital T p theta t xt minus 1 given xt over product of t from 1 to t, okay, q phi xt given xt minus 1. So in posterior distribution, we are proceeding the Markov chain in the reverse direction. In the likelihood, we are proceeding in the forward direction. So in the forward direction, we go from capital T to x naught, and then in the reverse direction, we go from x naught to x capital T. Okay. So now actually, since we have a product inside the log, we can break it up into sum of terms. And then what we'll try to do is that we'll try to combine the terms from the numerator and denominator, right? Because overall, for this looks like an expectation over capital T variables, right? And if you have to compute this expectation, suppose if you have to perform it using Monte Carlo sampling, you'll have to sample capital T variables, right? And if you do that, then you are essentially going to have high variance. So in order to avoid having this like big sort of expectation over capital T variables, I'll break it into sum of terms, and let's try to see how these terms evolve. So what we'll try to do is that we'll try to combine the terms which have the same variable in the numerator and denominator. Okay, so let's first expand it out, and then let's see how does it look like. So this is essentially expectation of q of x 1 to t given x naught. Okay, by the way, so when we talk about the variational diffusion model, so note that the distribution Q is not trainable at all. So there is no such parameter phi over here because it's a fixed distribution, and alpha t is also just a hyperparameter. So here essentially we don't have this variable phi. So now what I have is expectation of q of x 1 to t given x naught, and inside this expectation I have log of probability of x capital T times p theta t xt minus 1 given x capital T, so on up to p theta 1, and then finally I have x naught given x1, right? So we move in the direction from x capital T to x naught. In the denominator I have the terms q superscript t x capital T given x capital T minus 1, okay, and then all the way down to q1 x1 given x naught. Now what I can do is that I can start combining the terms from the numerator and denominator, and then I'll split this product. So first of all, we can combine this x capital T here and the x capital T term over here. The reason we are trying to do that is that we want to split this term, we want to split this sum, and we want to split it over terms, one for x capital T, one for x capital T minus 1, and so on, right? So next we can then combine, for example, this x capital T minus 1 given xt with qt of x capital T minus 1 given x capital T minus 2. So here basically in the denominator we are always conditioning on a variable of one lesser index, and in the numerator we are conditioning on a variable of one greater index, except for this x capital T term wherein there is no conditioning in the numerator, right? So essentially let's break it down. So what I have over here is this log p of xt over qt x capital T given x capital T minus 1 plus log p theta t x capital T minus 1 given xt, and then in the denominator I have q of t minus 1 x capital T minus 1 given x capital T minus 2, so on until we get to this term p theta x naught given x1. Since we don't have x naught as unconditioned in denominator, so we'll just get the numerator part of this. Right. So actually I'll request you to just break it up this term yourself and then verify, but try to see that we combine x capital T with x capital T term, x capital T minus 1 with x capital T minus 1 term, and so on. Okay, now once you finish this thing, what you will get is that you can write it as an expectation over q of x1 capital T given x naught. Okay, and first term is of the form log p x capital T over q T x capital T given x capital T minus 1. And then in the remaining terms, I have sum over T from 1 to capital T minus 1 log p theta T minus 1 log p theta T plus 1 of xt given xt plus 1 over qt xt given xt minus 1 term. Okay. And then I also have log of p theta 1 x naught given x1. Okay, so here what I have done is that I have just splitted the product into these sum of terms, and now I have expressed this sum in terms of the summation convention. There were two terms for which I needed to take care separately. One was this x naught given x1 term, and the other was this x capital T term. This x capital T term had to be taken out separately because it wasn't conditioned. This x naught given x1 term had to be conditioned separately because here I did not have a denominator counterpart. Okay, so now once I have expressed it in this form, what I can do is that I can write it as expectation over q of x capital T minus 1 x capital T given x naught log probability of x capital T over qt xt given xt minus 1. And now the thing is that, see, so here it's a expectation over all variables from 1 to capital T, but since in this term only two of these appear, x capital T and x capital T minus 1, I need to take expectation over only these two, right? And now if I consider this summation, which is sum over T from 1 to capital T minus 1, this expectation would be over x T minus 1, xt, xt plus 1, right, given x naught of course, and then log p theta T minus 1 xt given xt minus 1 over qt xt given, so numerator I have xt given xt plus 1, denominator I have xt given xt minus 1. Okay, and then finally I have the final term, which is expectation over q of x1 given x naught, and then I have log of p theta 1 x naught given x1. So here in the final term I have two variables x naught and x1, so essentially the expectation is only over x1 over here, right, because x naught is always fixed, right, when we are taking this expectation. X naught is basically my data which is already fixed. So essentially given data x naught, we essentially have these terms in my expectation. Okay, so basically we had split it up into these terms, and whatever variables appeared in the term, we took expectation only over those variables, right? So now let's look at each of these terms. The first term, right, which happens to be this x capital T over p over q of xt given xt minus 1. So note that x capital T was just normally distributed with mean 0 and covariance identity, and none of these distributions q had any parameters at all, right? So essentially all these terms, they will not have any sort of parameter, right? And so this term is actually called as the prior matching term, and while training it will not affect our gradients at all, right, because there are no parameters over here, so the gradient with respect to any parameter would be 0 for this sort of prior matching term. The next term which we see over here, which is xt given xt plus 1 over xt given xt minus 1. So this sort of term is called as the consistency term. And what it tries to ensure is that whether you get to xt from the next latent variable or the previous latent variable, right? Whether you get it from xt minus 1 or xt plus 1, the distribution should match with each other. So if I'm proceeding in the posterior fashion, I will go to it from xt minus 1, whereas in the likelihood fashion, I'll reach it from xt plus 1. Now both these distributions should be as close to each other as possible, and it tries to ensure that these are consistent, right? And this this final term which we saw over here is essentially the reconstruction term, wherein we try to reconstruct the image from the most recent latent variable, which is x1. Now the issue which comes up is that in this consistency term, I have an expectation over 3 latent variables, xt minus 1, xt and xt plus 1. Right? For the other two, it's an expectation only over 2 latent variables, or here in this case only over 1 latent variable, but here I have an expectation over 3 latent variables. Right? And this makes the training hard to perform. In order to circumvent this issue, we will actually need to break up the summation in a slightly different manner. So we'll see that in the next lecture on how to perform that. As far as this lecture is concerned, so basically what we have seen so far is that, okay, there is one way of splitting this term, splitting the summation. Now this leads to, a sort of a fancy sort of term which is actually difficult to estimate using Monte Carlo estimation, because it requires sampling 3 latent variables, which makes the variance large. So in order to circumvent this issue, we will actually try to split the summation in a slightly different manner, and we'll see how to do that in the next lecture. Okay, and that will also give us an algorithm to train this objective function. Okay, so thanks a lot and bye.